All right, so how to eat dinner there. Trying now to manipulate my computer. All right, so this is where I left off. I'll get through some of these, and you can do what you want with it. All right, so chicken pot pie for dinner. Daughter only ate the chicken. I don't know what's the matter with you kids today. Chicken pot pie used to be like a huge thing when I was a kid. All right, so properties of ionic and covalent compounds. This is where I left off. The state of matter at room temperature for ionic compounds, because of that attraction between the particles, are very frequently solid crystals, almost exclusively solid crystals. The covalent compounds, though, I changed what was on there. It's various. There's solids, there's liquids, there's gases from covalent compounds, but they're certainly not all solid crystals, as the case with ionic. Melting and boiling points, as we did in the lab, you hopefully learn that because of the ionic forces, the positive negative pulling on each other, it's hard to separate those particles to get them to melt, and even harder to get them to boil, so it would require a lot of heat. However, for covalent molecules, to separate one molecule from another molecule doesn't take much to overcome the forces that are holding those molecules together. You're not breaking the bonds, but you're holding the molecules, giving them more room to move around more. That's what melting and boiling are. It's more kinetic energy. So covalent bonded molecules will, between each other, have forces that we'll talk about in a minute here. But otherwise, they're low melting, low boiling, and we saw that in the lab. So solubility, ionic compounds dissolve well in water. Covalent compounds do not typically dissolve well in water. We saw that in class. I took a Advil or a Tylenol, crushed it up, or opened up a liquid gel and tried to mix it with water. And plus, some obviously covalent compounds do. We had sugar in your lab. We also had Truvia, which was the other stuff that we did that dissolved pretty well, but petroleum jelly wouldn't, cooking oil would not, which is covalent, and many organic compounds like we saw will not. Can they conduct electricity? Again, we did this in class. Ionic conducts it well. We drew it on the board that having a charged atmosphere in the water, if you look at that video about dissolving NaCl in water, that the particles separate. There's charged particles throughout the water, and that helps complete a circuit. Whereas in covalent compounds, because they don't have those charges, are not typically good at conducting electricity. So valence electrons are the outermost energy level. Lewis dot diagrams, we only show the S and P of the highest number. And you also know from the periodic table how many valence electrons each element will have based on what group it's in. Group 1 will have 1, group 2 will have 2. We're calling the transition metals 1 or 2. But anyway, here's an example. Every side of the element can hold 2 electrons in this Lewis dot diagram. And what we're showing you for this class is you'll just start someplace and go around 1, 2, 3, 4, and then you'll start doubling up 5, 6. So oxygen has 6. There will be 6 electrons around in that manner. So 2 will be paired and 2 won't be paired. Examples of silicon and bromine and strontium come here. Look at this beautiful stuff. Silicon, so again, sulfur, 6 valence electrons, so you go 1, 2, 3, 4, then you start doubling. Oops, I went a different way, didn't I? I went 1, 2, 3, 4, 5, 6, I guess. All right, so it doesn't truly matter at this stage how you go around it, but you want to show that this has 6 valence electrons and 2 sets are paired in this case. Silicon has 4 valence electrons. That is really ugly. So you put the symbol in the middle of silicon and 1 electron on each side represented by a dot. Bromine has 7 valence electrons. It's a halogen. It's in group 17. So you're going to have 1, 2, 3, 4, 5, 6, 7. And then strontium has 2 valence electrons, just the 2, 1 and 2, not paired or anything. All right, so the octet rule is that chemical compounds tend to form due to atoms gaining or losing or sharing electrons to accomplish the stable noble gas configuration. That would mean 2 or 8 valence electrons. For the most part, 8 valence electrons. Lithium loses one to become like helium. Hydrogen tries to gain one or share one to be like helium. And one more over there loses 2. I'm going to say beryllium. But anyway, but here's how it boils down. Group 1, the alkali metals, have 1 valence electron. They have a very low electronegativity, so they tend to lose that electron. They don't have a lot of love for it, as it were, and they form +1 ions. Alkaline earth metals are in group 2. They have 2 valence electrons. Again, a low electronegativity, so they tend to lose those 2 electrons and get a +2 ion formed. Transition metals, groups 3 through 12. For this class, we're going to just say they have 2, but I want you to know there is cases where they'll have 1 or 2 valence electrons, but regardless, a very low electronegativity, so therefore they will form cations. But as they are transition metals, and we discussed earlier with Roman numeral assigning for naming, they can lose 1 through 7, and you have to sort of determine how many they've lost based on the anion it's with. I don't think we're going to be doing that. You should know, though, this is why it happens. Boron group 13, they have 3 valence electrons. They'll low electronegativity, so they'll lose those 3 electrons to be +3 ions. Carbon and nitrogen for group 14, 5 valence electrons for group 15. They tend to, because of their intermediate electronegativity, they'll share. They could lose or gain, and these could gain, but for the most part, these are going to be sharing. But if they were to do ionic compounds, these would lose or gain the 4 electrons, and these would tend to gain 3 electrons to be -3. Oxygen group 16, has 6 valence electrons. Everything in that row has a high electronegativity for the most part. They tend to gain 2 electrons to be a -2. Halogens group 17 have 7 valence electrons. They have a high electronegativity. They tend to gain 1 electron to be -1. Noble gases group 18 have 8 valence electrons. Do not really have an electronegativity because they don't want to add another electrons, and they're typically stable. So they don't tend to make a ion of any form. All right, so that'll get us to molecular geometry. I'm going to stop here because much of this will be done elsewhere.